That's the one that you know a little bit about. So, somebody tell me, what is a pH? What does it measure? Yeah. Acidity. Okay. And then, kind of on the bottom end of that acidity scale, though, it's called a what? The low, if it's, yeah, the basicity. Did I say that right? Basically, it measures if something's an acid or a base. So there's the acidity of something, so how acidic is it? And there's the basicity of something, so how basic is it? Basicity. I'm pretty sure that's a word. You can check me if I'm wrong. I don't know. Anyway, so, no. So, what is the scale then for a pH? From what to what does it go? 0 to 14? Maybe. Okay, and what side of the scale is acids and what side of the scale is bases? So are like low pHs, those are what? And so halfway neutral is 7, right? So things get like more basic as you go this way, and things get more acidic as you go that way with what their pH is. Okay. Now, here's a question that you probably never had answered for you in chemistry class. What is a pH? They tell you how to measure it. They tell you, like, it helps you to decide if it's an acid or a base or whatever. But what is a pH? Where the heck do these numbers come from? Yeah. You're so close. Hydrogen ion. Is that hydroxide? Okay. So, yeah. And even then you're almost right. pH, it's the negative log of the hydrogen ion concentration. That's the definition of pH. So, how concentrated is this substance, whatever it is that you have, how concentrated is it with these little hydrogen ions in there? Okay? When you use the brackets like that in chemistry, that means concentration. Okay? And the little H plus is the hydrogen ion. So what is the hydrogen ion concentration? And then it is the negative log of whatever that is. Okay? And the answer to that puts you down into a pH. So if your hydrogen ion concentration is very large, you're either very acidic or very basic. We're going to investigate that in a second here. And if the hydrogen ion concentration is very small, then that pushes you to one end of the scale as well. Okay? So let's do a little comparison here. So what are some ones we've got? So vinegar. Those of you that have done stuff in science, is vinegar considered an acid or a base? Do you remember? It's an acid. Yeah, it's definitely an acid. Do you guys ever do those little, like, you put the vinegar with the baking soda and it goes, and it makes the little, you can do the little volcanoes, the vinegar, and nobody ever do that? The vinegar and the baking soda, and you put it in and it makes the volcano thing. It's because the vinegar is an acid and the baking soda is a base, and you put them together and they don't like each other. And no, okay. Well, anyway, vinegar is an acid, and its hydrogen ion concentration is equal to 3.98 times 10 to the negative third. And the unit for this is in moles per liter. Remember moles? Anybody? Anybody take AP chemistry? Maybe? You've seen it? Okay. All right. A mole is just a very, very large number. I don't remember exactly what it is, but it's just like this huge number because there's so many of them. But anyway, so 3.98 times 10 to the negative third, that's for vinegar. Baking soda, vinegar's rival with the volcano stuff. Its hydrogen ion concentration is 3.98 times 10 to the negative ninth moles per liter. Okay, so if something is acidic like vinegar compared to something that is very basic like baking soda, the hydrogen ion concentration, is it larger or smaller? It's actually larger. Okay, we got to know our scientific notation here a little bit to figure this out. This number, 3.98 times 10 to the negative third, that means you would take this number and move the decimal point to the left 3 places, right? And this one, you would move it to the left 9 places. So this is a smaller number than this one, right? Because the exponent technically is smaller, right? Negative 9 is smaller than negative 3. So baking soda has a very, very small hydrogen ion concentration. Vinegar is relatively big comparatively anyway. So so that's kind of one thing, one kind of a check, I guess. So if you're comparing to substances or whatever, and the thing that should be more acidic should have a larger hydrogen ion concentration. So more hydrogen ions that you throw in there, the more acidic it's going to be. Okay? Yeah?
Is it a coincidence that both of them are 3.98, or is that some kind of standard?
It's just because it ends up working out where they both come up with pHs that are like a nice, neat number when you're done. But I'm not entirely sure, though. So, because I think in moles, well, no. Yeah, I'm not entirely sure. I'm sure there is, but I don't know my science well enough to tell you why. In any event, let's see what the pH of each one of these is then, though. So the vinegar, we expect it to be somewhere between 0 and 7, right, because it's acidic. So negative log of 3.98 times 10 to the negative third. 2.4, is that what we got? Okay. And then, so this is for the vinegar. And then the baking soda, we would expect the pH to be something between 7 and 14. So negative log of 3.98 times 10 to the negative ninth. So 8.4. Okay. So, one question that you might get asked with this type of a thing is, how much more acidic is vinegar than baking soda? So, like, how many times more acidic is it? Okay? So, consider this for a second. Because this is a log that we're using to get the pH, okay, you could take a look at these two numbers and say, well, the vinegar has a pH that is 6 pHs, or what do you want to call it, 6 pHs less than the baking soda. So how could I use that? Well, this is a log base 10, right? So every time the pH goes up by 1, it's actually going up by a factor of 10. Okay? So if the difference in the pH is 6, let's jot that down. So difference in pH, 8.4 minus 2.4, so that's 6. If the difference in the pH is 6, what's actually the difference in the acidity then? Yeah. It's like a million, right? 10 to the 6th. You have to kind of undo that log, right? And how do you undo a log? You make it an exponential. So it's a base of 10, right? So 10 to the 6th. So 10 to the 6th is a million. So how many times more acidic is vinegar than baking soda? It's a million times more acidic. Okay? And that's why they have this on a pH scale instead of just saying, well, just always compare the hydrogen ion concentrations. Well, then you're going to get comparisons from one thing to the next that are like huge, like 1,000,000 times more. Are you serious? So instead of doing that, they kind of shrinky-dink it down a little bit and say, okay, let's go factors of 10. Every time you jump up 1 in the pH scale, you're actually going up by a factor of 10. Or I guess going down by a factor of 10 as far as the city is concerned. But in any event, this is how you can figure that out, though, to make a direct comparison of the acidity of one versus the other. So we can say that vinegar is 1,000,000 times more acidic. Okay, so vinegar is 1,000,000 times more acidic than baking soda. And on the flip side of that, you could also say that baking soda is 1,000,000 times more basic than vinegar is, if you're going to go that direction with it too. Okay. The idea, though, when you're using a logarithmic scale that's using a common log, means every time you go up 1 in the scale, it's a factor of 10, factor of 10, factor of 10 to get there. Okay. So earthquakes, the Richter scale. The Richter scale works the same way. Every time you bump up 1 in the Richter scale, to like a Richter scale of 3 versus a Richter scale of 4, how many more times intense is the 3 versus the 4? 10 times. Okay? And then a 3 versus a 5? 100 times. 1,000 times. 10,000. It's the same kind of thing. Okay? So if we want to compare some earthquakes, we got to kind of think of it that way. All right? So let's do some Richter scale here. Make sure I'm spelling this right. No, it doesn't even give it to me. Okay, so I think this is how you spell it. It's like Richter, pretty sure. Yeah, got it right. Okay, so ever wonder exactly how they get those numbers for the Richter scale? Well, there's an equation they use to do that. And it uses a logarithm. Mm-hmm. Yep. Anytime you want to compare, like these common logs, they call them common logs because they're commonly used. But anytime you want to compare something that like could vary a ton, kind of like the pH thing, because like 1,000,000 times more, there's huge differences. Usually logarithms are brought in to bring the scale down so that it's easier to kind of digest and look at like, oh, that's a 3 versus a 5, okay, rather than, that's a 2 versus a, 2,000 or whatever. So the Richter scale, they do the same thing because earthquakes can vary wildly from one to the next. And so putting it on a scale that uses a log brings it down to just, 1 through 7 or whatever it is. So in any event, so the R, that's the Richter scale value that you would like hear in the news or whatever. The A is, I believe, the amplitude. Yep, amplitude of the wave created by the earthquake. And it's always given in mu m. Anybody know what that is? What unit that is with the mu m? No? Okay, it's all right. It's micrometers. And by the way, a micrometer, as you might expect, is super tiny. And some of you guys might be thinking like, oh, hold on a second. So we're talking earthquakes. I mean, earthquakes knock buildings down. And we're talking about micrometers as far as the amplitude of the wave. Okay? Well, think about that. Yeah, it's really small, but the crust of the earth is literally moving up and down when this happens. Okay? So when the entire crust of the earth moves up and down a micrometer, crazy stuff still happens, though, because everything is sitting on it still. Okay? So a micrometer is still significant when you're talking about an earthquake. So, but yeah, so that's how that gets computed. And then the T, that's the period of the wave. Okay, and so the period of the wave would be like, how far does it go out? So like from the epicenter of wherever the earthquake is, so how far does it go before it repeats itself again? So it's kind of like the crust of the earth does this kind of like wave thing out from the epicenter of the earthquake. And the amplitude is like how high up it goes. So it's this micrometer tiny little bit. and it just goes way out from the center of wherever that happens, and it just keeps moving the crust up and down as it continues out. So if we know the period, we know the amplitude, and then there's this B, and what happens is as these waves go out, they don't just continue forever, right? Because then if there was an earthquake in San Francisco, we'd feel it in Hopkins, and that's not the case. It's as it goes out from the epicenter, what happens to that wave? It dissipates, right? And so this B that gets added onto the end is just a number that accounts for how much it dissipates as it goes out. Okay? So, I don't know if they really give a unit for that. No.
So are we taking the log of that whole thing, or is it the log?
Nope. Just the log of this, and then plus B. Okay, so that B, that's just a number depending on the earthquake that you have that accounts for the dissipation of the wave. Okay, so it'd be some different number that would get put into there. So, so what we're going to do is we're going to compare a couple of earthquakes, use the log definition to take a look at what their Richter scale values would be, and then kind of compare the two. So, all right, so let's do that. So let's say an earthquake has an amplitude of 5 micrometers. Let's see, a period of 30 and B equals 0.3. Okay, so then another earthquake has an amplitude of 7 micrometers, period of, let's say, 15, and B equals 0.2. So then the question becomes, which of the two earthquakes, we'll call this earthquake 1, earthquake 2, which of those two earthquakes is more intense, and by how much? Okay. So, which is more intense, and by how much? All right, so earthquake number 1, the Richter scale value for this guy is going to be the log of A, which was 5, over T, which was 30, plus 0.3. All right, so let's see what we get from that. Oops, okay. I made up some bad numbers. We're going to change up two things here real quick. This is what I get for trying to make up numbers on the spot. Make it a 50 and a 70, not a 5 and a 7. Because we're going to get Richter scale values that don't make no sense if we do that. First one's going to be 50 over 30, not 5 over 30. All right, we got 0.52. So that's a pretty weak one. Second one, it's going to be log of 70 over 15. plus 0.2. So that comes out to about 0.87. All right, so both of these are pretty weak earthquakes, but the question still is how much more intense is the one compared to the other? Okay, so first thing we need to do is, kind of like we did with the pH, just what's the difference in the two Richter scale values? Okay, so 0.87 minus 0.52. So we end up at 0.35. But the Richter scale is a log base 10, right? So it's not actually 0.35 times as intense. How would we calculate that? 10 to the 0.35, right. So apparently, number 2 is about 2.24 times as intense as earthquake number 1. Okay? All right, so just kind of keep in mind, like we talked about, it's a logarithmic scale, so it's got to be, and these are common logs that we're using here, so it's got to be 10 to whatever. Okay. Let's take a look at here is, let's do a little work in the kitchen. We're going to talk about putting something in the oven. Actually, this applies to, you could put something in the refrigerator. It's called Newton's law of cooling. It's actually pretty handy if you ever want to figure out how long you need to leave something in the oven to get it to a certain temperature, or how long you need to leave something in the fridge to get it to a certain temperature. It's called Newton's law of cooling, but actually it could also be called Newton's law of heating. It's just kind of this whole temperature thing that's going on. So in any event, so here's what he's got going on. So there's this equation that I'll just write out for you here first, and I'll explain what all these little variables mean. Okay, so the big T here, that is the temperature after a certain amount of time. Well, because they're all temperatures, but they're all temperatures of different things. So I know that's kind of confusing, but so T sub M is the temperature of the surrounding medium. Okay, so key word in that phrase, surrounding. So if I have like a pie and I'm putting it in the oven, what is the surrounding medium? The temperature, yeah, whatever. The temperature of the oven. 350, I'm putting it in, yeah, right. Okay, surrounding medium, what's surrounding the pie as it's cooking? It's the whatever, or if I'm taking the pie out of the oven and it's too hot, I'm going to put it in the fridge to cool it down. It's the temperature of the refrigerator. Or if I'm just leaving it in a room to cool, it's the temperature of the room, wherever it is. Okay, the surrounding medium. Then this little T, it's called T naught, but the T with the little zero there, that's the initial temperature of the object. And like you've seen before, the lowercase t, that's simply time, however much time has gone by. And the k is some constant that changes depending on where you're at. Yep. It doesn't have, the thing is, it almost kind of seems like a random number, but depending on the situation, k can be a lot of different things. But it doesn't actually have like its own meaning, though. You know, I can't say, oh, k is 0.2. That means there are 0.2 dust particles in the air or something that I've measured to get that 0.2. It doesn't actually, it's not a physical anything, but it's always there. It's just a number that's always there. So we have to include it. I'll show you. We will do that together. Yeah, I'm sure excited. Okay, so let's try. Okay, and we'll show you how we can apply that formula. So let's say I have a hard-boiled egg. You could call it a pie if you want, I guess. I don't know. That starts at 96 degrees Celsius, is placed in 16 degrees Celsius water to cool. So later, the egg is 45 degrees Celsius. So I want to know how long until the egg is 20 degrees Celsius. Let's say 20 degrees Celsius is like that perfect temperature just when you want to eat it. And I want to know how long do I have to wait for this egg before it's good for me to eat it. So that's what we're going to do. We're going to use Newton's law of cooling to figure out what that time would need to be then. Okay? So, all of the information. Yep, so we'll sit down with our pencil and paper while we're waiting on our egg, and we'll figure it out. No. Once you're really good at this kind of math, you can knock this out way before that egg's ready to go. So, okay. So let's see if we can take the information and like kind of encode it a little bit or decode it. What is what? Okay, so what is the temperature of the surrounding medium? 16. Yeah. And what is the T naught, or is the initial temperature? 96. Yeah. Okay. And then what is the just regular T? What was that? Temperature of the object after a certain amount of time? 45. Okay. So let's see. When I said later, sorry, I needed to give you a time. It took 4 minutes for it to get to 45 degrees. That's important. You need to know how long it took to get to 45 so we can figure out how long it's going to take to get to 20. So, yeah, that was 4 minutes. So little t is 4. So, do you guys see how I have basically everything in that equation except for k now? So by plugging all these numbers in, I can find k. And once I have k, I can do it again to figure out the new time. That's kind of the approach here. So let's try. So 45 equals 16 plus 96 minus 16 e to the negative k times 4. Okay, so 45 equals 16 plus 80 e to the negative 4k. Be careful you don't add the 16 and the 80, right? Because they are not like terms. What do I have to do to solve this next? Subtract the 16, yep, and then divide by 80. So I'm going to do those two steps at one time here. So 45 minus 16 gives me 29. 29 divided by 80 gives me 0.3625. Okay, I've got a number equal to e raised to something. Natural log time, yep. So the natural log of 0.3625 equals negative 4k. And if I natural log that thing, I get negative 1.01473. And then I just divide by negative 4, and that should be my k. So it looks like we're getting a k that is somewhere around point, we'll take it 3 decimal places here, let's say, so 0.254. Okay. Now, I want to figure out how long it's going to take to get to 20 degrees. So my time now is going to start after the egg is at 45. Because I already knew it was 4 minutes to get from 96 to 45. So now I want to know, okay, so from 45 to 20, how much time is it going to take? Yeah. The 4? Put it here. Wait, where? This one?
It's like T of T equals T of M plus T of O minus T of M.
It's not, well, it's not T of M, and it's not T of O, but this T of T, just think of it like, because it's a function of T, that's why that was in parentheses, so it's not multiplied by 4 there, it's just as a function of T, so you can just like kind of ignore this and just think big T equals and do it that way, so it's just 45, it's not times 4 or anything like that. So in any event though, so we're starting now, we're kind of starting the clock over again, so from 45 degrees to 20 degrees, how much more time do we have? So we're going to go back to this equation, but some things are going to change this time. Yeah?
How does that work, though? Because your water would be warmer if your egg got colder, because you have to transfer heat somehow from the egg.
Right, and this accounts for that.
Does it?
Yeah, it does. Yep. So this new equation then, my T, okay, my new temperature is going to be what? 20. Okay, so I'm going to do the same little list like I did before. So that's going to be 20. The initial temperature of the egg now, 45. And the temperature of the surrounding medium, even though heat has been transferred, this accounts for it, but you still have to leave that as a 16. Okay? And my time, that's what I'm going to try and find now. Okay? So we're going to go back in one more time, plug our numbers in and see what we got. So my final temperature, 20, equals 16 plus initial temperature now is 45 minus 16. E to the negative, oh, yeah, we got that. It's not 4 anymore, right? It's this negative 0.254 T. And it's really kind of the same process. I mean, like, algebraically, it's still the same. You're just, now you're solve it for T, okay? So if I subtract the 16, I got a 4. 45 minus 16 is 29. So I divide by 29, 0.1379 equals e to the negative 0.254 t. So natural log that. And then I divide. It's about 7.8 minutes. Okay, so now you got to be kind of careful about how the question is worded here. So our original question, how long until the egg is at 20 degrees Celsius? Well, if you wanted to know how much longer it is after it's at 45 degrees, what's your answer? 7.8 minutes. If you wanted to know, like, start to finish, how long did it take to get to 20 degrees? It'd be 7.8 plus 4, right? You had that initial 4 minutes plus the other 7.8, so it's, like 11.8 minutes or whatever. So the way that this thing is worded, how long until the egg is 20 degrees Celsius, that would be the 11.8 then. If it says, like, how much longer, then it would be 7.8. But total time, 11.8 minutes. So did it take us longer than 11.8 minutes to do that problem? We can still enjoy our tasty egg because it didn't take us too long to do our math. Yep.
Yeah, that's all you would have to do.
Well, you have to peel the egg. You gotta wait 4 minutes to get this.
Oh, do you have to? That's true. You'd have to wait 4 minutes to take your data to figure out what the other temperature was. So you have 7.8 minutes to do your math. Math, maybe we did. I don't know. Anyway, that's all I got. So I'm gonna let you on your homework.